Howdy folks, welcome back to another CS 128 Honors Lecture. Today we're going to be covering generic types and smart pointers in Rust. So we're going to start off by answering some more of your questions and then go into some struct review, so cover some stuff that we learned in the last two lectures, and then introduce you guys to generics and how you can reproduce code using some simple techniques. And at the end, I'm going to introduce you guys to smart pointers, and all of this is going to build up to some homework 8 hints. You guys are going to be implementing a linked list as part of your homework, and so parts of this lecture will be dedicated to helping you guys out, giving you guys some sort of structure to your code, and helping you guys get started. All right, a couple of quick reminders. Homework 6 is due today at midnight. Let us know if you need an extension. Homework 7 is due on the 1st at midnight. Homework 8 releases tonight, due on the 3rd. Homework 8 is the linked list homework, so stay tuned for parts of this lecture for tips on how to get started. And MP2 is due on the 4th at midnight. Okay, let's get into it. So we know that the MPs can be challenging. Ownership can be difficult to deal with. Borrowing can be hard. It can be hard to fight the compiler with all of these warnings that it throws. But I strongly recommend you use an IDE and you take advantage of the IDE. It is there for a reason. It is we tell you to develop locally in an IDE rather than on PrayLearn because of the hints it gives you, and it will make you so much more productive by knowing how to read the compiler hints and working from there. So again, these tools are here to help you, so use them. So biggest takeaway, use an IDE like VS Code, use the Rust Analyzer extension, link to that is at the bottom of the slide. These tools are here to help make you more productive, so use them. So the MPs and the homeworks can be very intimidating, especially homework 8, but reach out to us in office hours, reach out to us on the Discord forum. We are here to help you guys out. We're here to help you learn Rust, and so take advantage of this. Take advantage of office hours, take advantage of the Discord forum, learn from your peers. That's the only way to get better. All right, so briefly reviewing struct methods, you use the fn keyword, very similar to normal functions. Struct methods will contain code that is run somewhere else, similar to functions, but you define struct methods in the context of a struct or enum. So you use the impl keyword to implement methods for this custom type. So the first parameter is almost always self, or a borrow to self, which represents a borrowing of the instance of the struct this method is being called upon. So there is also the type of associated method, which does not take in self, but normally is used as a constructor and returns an instance of the custom type. Okay. And a quick review on self. Ampersand self is an immutable borrow to the current instance of the struct, say like something to retrieve some piece of data from the struct or perform some computation upon it. And ampersand mute self is a mutable borrow to the current instance of the struct, and this is usually used to mutate the inner contents of the struct, some sort of object-oriented state-based programming. And so you use dot notation on self to access both the struct fields and call other struct methods within the impl struct methods. Okay, so with that, let's get into generics. So generics allow you to generalize types to broader cases. It allows you to write less code while also having more functionality with your code. What does that mean? Well, you're able to make a vector, per se, of multiple different types, of integers, of strings, of booleans, whatever you can think of. And there is no single implementation for strings. There's no individual implementation for integers. There's no individual implementation for booleans. It is generalized to work for all types. So generics allows you to do this. They help in reducing code duplication. They shorten the amount of code you have to write, but give you a lot more functionality. So generic type parameters, as they're called, are usually represented as the angle bracket t. And you've seen this in vec_t or hash set t in MP1 or MP2. And so this t is usually replaced by a actual concrete type, as they're called. So strings, characters, integers, any defined type that is not generic. And so generic type parameters can accept one or more parameters. So t, you can have two, like in the result type, te, we'll get to that in a sec. But, generic type parameters, you can have one or more different types. And like I said, if a type is not generic, it is concrete. So strings, integers, your own custom structs, those are concrete types. And like I said, you've seen these before. You have option T, an optional element that can either have some element with type T or no element with variant none. And the result enum, you can have some result with a success value of type T and some error value of type E. And so you're able to reproduce code using these generic elements. And like I said before, vec_t, you have an ordered collection of elements, all of the same type T, so a vector of strings, a vector of integers. There's only one definition of vector, but you're able to write vectors of multiple types of strings, of integers, with just this one sort of class. And like you guys have seen in MP2, there's the hash set, which is an unordered collection of distinct elements of the same type T. So you cannot really index it the similar way as you would with a vector, but you can, in O1 time, insert elements and check if the set contains elements. And also the hash map. You'll be using this in MP3. It is similar to a hash set. It's an unordered collection of distinct keys, but the keys map to a value of type V. And so the thing to note is that K and V can be the same type, but there is a distinction. They could also be different types. As is the case with results, T and E could technically be the same type. It's just that they are also allowed to be different types. But in the case of option, in the case of vector and hash set, all elements must be the same type. This double generics just gives you more flexibility in scoping out your code. And like I said, hash maps will be useful in MP3 when you guys start to implement MapReduce. So in Rust, there are 3 different types of ways to use generics. You can use them in your own custom types, structs and enums, as you've seen in the standard library with vectors, hash maps, hash sets, etc. You can also use generics in functions. You can have a generic function that acts upon a bunch of different types of data. You only have to write the function once with the generic type. You can also template interfaces with generics, so traits. We will get more into this in the special topics section of this class towards the end of the semester. But right now, we're going to focus on simply implementing generics on custom types, so structs and enums. So from the last 2 lectures, you guys have seen how to define your own custom types, define your own custom structs, and implement some struct methods on those. So we have this basic struct val, which contains a single value, which is double, and we're implementing a method on that to get a borrow of the value owned. So we use this impl keyword on the custom type and use the fn with a immutable borrow to self to access that data. With generics, you use this sort of turbofish bracket, the name of your struct, and then in angle brackets, a T to indicate that you have a generic here. And you can use this generic as a type. And so the value contained inside my struct is of type T. And so if I decide to make a generic value that is an F64, T will be an F64. I could also use a string. In that case, T would be a string. A generic value would contain some string data. Another distinction is that when you're calling impl, you have to specify T within angle brackets after both the impl and after the struct type. So you're implementing generic methods on a generic custom type. And so we have this similar template function. Value returns a immutable borrow to the value contained inside the struct. Again, we're using ampersand self to access that data. And so you might already be familiar with how to use these turbofish brackets. You use them with vectors. You probably use them with hash sets if you started MP2. You simply specify the struct name, then in these brackets, you put the type you want it to contain. So if we were using this basic struct val, we do not need to do this. We can just directly specify that val is 3.0 and F64. But if I want to use a generic type, something that is reusable, I have to specify the value, the type of the value I want to use in these angle brackets. But what you can see is this allows us to reuse code. So rather than writing a struct for strings, a struct for doubles, a struct for booleans, we only need to write one struct, this generic type, and we're able to reuse that code as many times as we want for different types, which is an extremely powerful tool. So I want to sort of demonstrate how to do this with your own custom types by recreating the option enum. You guys are probably familiar with this already. We've made you use this in a bunch of different homeworks and MPs. The option enum has two different variants, sum or none, where the sum contains some value inside. So do enum variants sum, it contains some type here, leave that blank for now, and none. Remember, when we want to create our own custom generic type, after the type name, we specify that we're using this custom type t. And I want to also note that this t can be anything. T is simply a convention. I could make this type. I could make this very cool type. The name can be anything as long as it's consistent. It's just that t is the convention. There we go. And so we can pass in this t into our struct, because into our enum variant, because the sum enum variant will contain a piece of data of type t. Okay. And so when we are implementing methods on this generic type, we are implementing generic methods upon a generic type. So we have t in angle brackets after both the impl and the custom type. Okay. So you're probably familiar with unwrap already. Unwrap will attempt to get the data inside sum, but it will panic if the enum variant is none. So let's see how we can do this. I assume that we'd use a match statement because we are matching against an enum. Match self type. So self refers to the instance of the enum, so either sum or none. So in our match cases, we have sum, which contains a value v, for now, or none, which does not contain any value. So as per the description of the unwrap function, we'll panic if we ever hit this case. So I strongly advise that you never, ever use this in your code. Panicking should be avoided at all costs. It's just that this is a convenience method, and it should only be used when you're 100% confident when you have a sum variant. Okay. And so when we have sum, we will return that value. So as you can notice from my little extension here, sum takes in a value here, and is a reference to this type. So I can simply return that reference at the end. Okay. And so the compiler is warning me because in my enum variants, I have to specify that I'm matching against my option, not the built-in option. There we go. So we can use this similar matching approach to tackle this isSum method, which simply returns a Boolean depending on the result of this variant. So again, match self, and we have two different variants this time. We can copy and paste that. And so, but we do not care about the value contained inside sum. All we want to do is check whether the variant is sum or not. So we can use this underscore to just ignore that value. So if we have a sum, we'll return true. If we do not have sum, we'll return false. And you'll notice that I'm using this isNone method to just refer to the isSum method. So isNone, it's just the opposite of isSum because there are only two enum variants. So I can just take the negation of the isSum method and use that as my implementation of isNone. Okay. So I have some testing code here. I have a my option enum variant that is a sum type that contains a string, CS128 honors, and I'm going to call this isSum method to check whether I have some, if I have a sum variant, and if I do, I'm going to unwrap that and print out the value. And after that, I have an empty or a none enum variant, and when I try to unwrap this, my code will panic, and you'll see that. So, cargo run binary called my option. Oops. there we go. So in this first case, we have this value, CS128 honors. My enum variant is sum, and so I'm printing out that we found some value. But then when I try to unwrap this, this none variant, my code will panic. There's an explicit panic because I called the panic function right here. Okay, let's go back. All right, so now we're going to move on to smart pointers. These are going to be super applicable to linked lists. We'll get into the reasons why. So you're probably familiar with pointers. You can come from a C or C++ background. Pointers are just variables that contain some address in memory. And at that address, there's some piece of data that the pointer points at. Smart pointers are effectively the same. They have some address that points to some piece of data in memory, but smart pointers are essentially data structures that contain additional metadata and functions that you can perform upon the data and metadata. So you've seen these before. You've seen the string and vector types. They are examples of smart pointers. They point to some piece of data, some array of either characters in the case of string, or an array of t, some generic type, some array in the heap. And these two types manage their own memory. So you do not have to worry about this array. You don't have to worry about what happens when the string goes out of scope. They will drop their own memory in the heap when they go out of scope. So that's the benefit of smart pointers. And they contain additional metadata. They contain some information about the size of the type or of the array. They contain some information about the capacity. And so they know when they need to make their array bigger to accommodate more elements. So another thing to note, smart pointers take ownership of the data they point to. This is going along the resource initialization, or resource allocation is initialization. Some of the more central high-level concepts of Rust is out of the scope of the class, but something to look for. Okay. And as I mentioned, when smart pointers go out of scope, the data that they own is dropped. So smart pointers are simply some piece of data on the stack. They contain the address and whatever metadata that they have. But when that stack data goes out of scope, the data that it points to in the heap will also be dropped. That is the important thing. Okay. And so one of the most common smart pointers in Rust is the box smart pointer. Boxes allow you to simply store data on the heap with no overhead. So there you have a pointer to this heap data that's on the stack, and you have this heap data in the heap that is of some unknown size. And so when the pointer on the stack goes out of scope, the data on the heap is free. What do we mean by this? Well, this is our box. We have some pointer here on the stack, and this pointer will point to some piece of data on the heap. Box is generic, so this data can be of any type. And so at the end of, say, some function call, at the end of main, when my box goes out of scope, this data here will be deleted from the heap and available to use from any other process or thread or whatever the program may need it for. So how do we use boxes? What do we use them for? Well, we can just open them up and put stuff inside them, but that is not in the Rust world. We really mean the box type in Rust. So you can create a box smart pointer using box : new. Again, this is the associated function that we introduced in the last lecture. You call box new, and then place whatever piece of data you want in here. This is generic, so it can be a string, an integer, your own custom struct, whatever you wish. Data will take on that type. And so if you want this data on the heap to be mutable, you have to make the box variable mutable so that you can access and change the underlying data. And so when you want to get access to the data pointed at by the box, you need to dereference the variable, dereference the smart pointer, similar to a mutable reference. The only caveat is, if you're calling a function on the data, you do not need to dereference the smart pointer. Rust will automatically do this for you. So if you have some data here, some string data, and you're calling a function on it, say push string, to add new characters to the end, you do not need to dereference the pointer. Rust will do that for you. But if you wanted to completely change the data using, say, the equals operator, then you would need to dereference the pointer and change it as you wish. Okay. Let's get into a brief example of how to use boxes. So I have this box here. Again, I'm using this generic format that, in this case, I'm wrapping a unsigned 8-bit integer with a box. So I have some piece of data on the heap that stores an integer, and B here, this is a variable on the stack that points at this heap data. So I simply call box : new and pass the data that I want on the heap inside that. So I can print that out. And then, if I want to change this data, I have to dereference the smart pointer in order to do that. Okay, so I can run this and show you what it looks like. So there you go. At the beginning, I have 100, and I am dereferencing the pointer to get access to this data, changing the data, and then printing it out again. We can do this with strings as well. So I have a box that points to a string on the heap, and I pass in the value I want string to take on, so CS128 honors. Okay. And so I'll print that out. And then if I want to change it, I can dereference the smart pointer and set it equal to a new string, whatever my string may be. But I want to show you in the case where you do not need to dereference the pointer. Say you just wanted to call the push string method on this. So you could just say b.pushString and add some more characters to it. So is the best. And so Rust allows this. Rust will dereference this pointer for you and call the method upon it. So we'll run this again. There you go. So CS128 honors, and then Rust will dereference this B pointer for us and then push some characters to it, and we can print out the data again. Okay. So you'll use the box smart pointer in a couple different scenarios. So you'll use it when you have a type that you don't know how big it is at compile time. I'll get more into detail about this in just a sec. The other sort of use case is when you have some type of value and you want it to implement a specific trait. So these are called trait objects. You want to create an object out of some common behavior. And so we'll get into this again in the object-oriented programming special topics section, but this is a super, super cool usage of box. Okay. So I wanted to talk about linked lists briefly because you'll be seeing them on homework 8, and the example we'll get into also covers linked lists. So linked lists are this data structure that composes a list that has some link in the list that contains some piece of data, and then a pointer to the next piece of data. So I have my link here, data, pointer to the next piece, and again, this repeats. And at the end, this pointer, there's no more links at the end, so I can point to none, or null, whatever it may be. In Rust, there is no concept of null, so we'll be using this none option variant. And you refer to this list using the head. We have this pointer to the front of the list, and we can use this pointer to go through our list and check the first element, check the second, and so on and so forth. And we can represent this with a struct in Rust using generics. We can use generics to make our list contain any piece or any type of data that we want. So we have this thing variable that is of type T, and T can be any type we want, such that the type implements display. So we're able to print out that type, just for convenience sake. And then we have this next pointer, which is an option enum that contains a link. So either none or some reference to a link here. So there is an issue with this though. Rust does not know how big this is at compile time. We don't know how big it is, so we can't put it on the heap, and this code won't compile. So if we were to try to compile this in VS Code, Rust would spit out this error. This recursive type link has infinite size. What does this mean? Well, link is recursive because it contains itself, or a variable that is of type itself within itself. You can get that sort of recursive style. So a link contains a link, which contains another link, which contains another link, and so on and so forth. You can see here we have the first link, and then the second link, and the third, and the fourth. And it has the possibility to repeat infinitely. And so Rust doesn't know how much data to allocate for this when putting it on the stack. And this is a problem, considering how Rust manages or aims to be type safe and memory safe. So there is a way to do this. There is a way to fix this, and Rust suggests that here. You can wrap this option in a box type. So rather than having a link here, you just have a pointer. And this pointer points to somewhere on the heap. It doesn't matter how big that is. The heap data can be of any size you want. That is the important thing. Box allows us to deal with these recursive types. Okay. So let's get into linked lists and see how we can solve this problem. So this is the struct you'll be seeing on the homework. You have your linked list here, which contains a pointer or some piece of data that points to the front of your list, and then the length of the list. And then each link is composed of some variable thing that is of type T, any type of data, whether that be strings or integers or booleans, whatever you want to use with these angle brackets. And then a option enum that can point to some other next link data. And we're fixing this compile issue by wrapping the link in box. So this no longer becomes recursive because we're wrapping this link with a pointer, with a smart pointer. Okay. So you guys will be implementing this class as part of your homework. I will let you write the new, the length, and isEmpty functions yourself, as well as the add front. I'll be sort of walking you through this add back function. So I want to start off by looking at this print function. Print will go through our linked list and print out each element. And we want to sort of copy the style as we approach add back, because the linked list only contains a pointer to the front of the list. And so we have the front, but we want to add to the back, which means we have to take the front element, find the last element by following this next pointer, and then finally changing what the next pointer points at. So how can we do this? Well, I'm going to start off by just incrementing the length variable by 1. Okay, plain and simple, just so we don't forget, because we do need to keep track of the length. Okay, and there is 2 separate cases of linked lists. One is when it's empty, and you need to change the head pointer. So you need to change what the first element is pointing at. So from none to some data. So if my first element is none, I'm going to change my front to a box. So to some piece of data on the heap. So this is a very verbose line of code. Essentially it's saying we have some element, it's not none anymore, and we're going to make that some element a smart pointer to some link on the heap. Okay. And then we added our element because we saw that the front is none, so we can just return after this. So that is our sort of edge case that we've handled. So then we need to traverse our list if we do not have a null at the start, and we need to find the last element of the list. So we can do that by creating this variable to keep track of where we are. So I'm going to make a mutable variable to the current link in our list that we're at. And because we need to change the last element of the list, I need to make a mutable reference to that piece of data. So it's going to be an option of a box of a link of some type T. Okay, and I'm going to start off at my front pointer. So start off at the front, iterate through the list, similar to this pattern here. So while my current variable is sum, I can either print it out and continue on to the next. So we're going to take this similar pattern into a while loop here. So while the current pointer is sum, we're not at the end of the list, we're not at none, and we're able to go to the next element. That is an important distinction. We want to change the last piece of data in the linked list, and so we need to make sure that we can go to that and dereference it and unwrap it. So we're going to take the current link that we're at, get it as a reference, unwrap that and get the next pointer. Make sure that it is sum. Okay. This is a very verbose line of code, which is why we're sort of helping you out here. Effectively, we're getting the pointer to the next element and making sure that it exists, making sure that it is sum so we can use it. Okay. And so we have our mutable variable here. We're going to go to the next element in the list because that we know it exists with this condition. So we're going to take a mutable reference to the current. We're calling this as mute method so that we're able to change it in the future. Change the pointer, change what the pointer points at. So unwrap that, and then make it go to the next element. Okay, almost done here. So effectively, this loop will stop once we're at the last element of our linked list. Once we're no longer able to go past, because the next is none. So that means that current will be whatever we want to change, whatever we want to change that to point to the new element. So take the current as mutable, unwrap that, and take the next pointer and set it equal to this new link. So copy this over. We have sum box new link. Okay. And I've written out some test cases here. So we're going to print out the empty list, then add to the back using our new function here, add to the back again, add to the back again, and then add to the front, finally add to the back. So our list should look like 1, 2, 3, 4, 5 if we've done this right. And there we go. Code works. We add 2, add 3, then 4, then add 1 to the beginning, and finally add 5 at the end. All right, that's all, folks. This one went a little bit long, but it should help you guys get started on homework 8 and give you guys some hints on how to approach the other functions. All right, take care.